A car is traveling along a road winding around the seaside cliff at 54 kilometers per hour. The road has an upward slope of 5 degrees to the horizontal. On a particularly sharp curve, the driver loses control, drives off the road, and becomes airborne. If the cliff is sheer so that it can be assumed to be vertical and is 40 meters above the ocean below, approximately how far in meters from the coast does the car hit the water? Okay, we gotta convert this 54 kilometers per hour into units of meters per second. We know that kilo means 1,000, so we're just gonna go ahead and add 3 zeros right after the 54. And now we have meters over hours. Okay, so now we gotta convert the hours to seconds. So we know that 1 hour equals 3,600 seconds. So now we have meters over seconds. Okay, so now in this problem, since the driver is going at a 5-degree incline, we're going to have a y velocity and an x velocity. So we're going to need to break that up. So we know that sine is opposite over hypotenuse. So we're going to use sine to find the Vy. And we know that cosine is adjacent over hypotenuse. So we're going to use cosine to find Vx. Okay, so when we do sine of 5, we get 1.31. When we do cosine of 5, we get 14.9. Okay, so now that we got the conversions out of the way, we got to figure out how exactly we're going to solve this problem. We're trying to find how far from the coast does the car hit the water. Now, because this is going to be a projectile motion problem, we're going to need some type of key component, so time, to figure out how long it takes to get from here to here, which is going to be the same as the time it takes from here to here, because the x and y components are connected by time. What we have right now is we have this equation, and that equation is going to help us find time. So using our y components, we have the 1.31 meters per second. I'm going to go ahead and set this equation up. 1.31 t plus 0.5 times negative 9.8 t squared. Our negative 9.8 is gravity because that's the only acceleration in the y direction. And we can set that equal to our initial distance of 40 meters because he's starting at 40 meters and then he's dropping all the way down to sea floor. So we can go ahead and do 0 minus 40. Now when we rearrange this, we get 1.31 t plus 0.5 times negative 9.8 t squared. And then we're going to add that by 40. So now we can find out our t value by using the quadratic formula, which is negative b plus or minus the square root of b squared minus 4ac. Divide all of that by 2a. Okay, so our a is going to be this part, and our b is going to be this part. So this is going to be b, and this is going to be a. Okay, so we can go ahead and rewrite everything in terms of this formula. So we have our negative 1.31 plus or minus square root of 1.31 squared minus 4 times our 0.5 times our 9.8. This is going to be a negative. And then we're going to multiply that by 40 because our c value is going to be this 40. Okay, and we're going to divide everything by 2 times 0.5 times negative 9.8. Now when we plug that into our calculator, we get 0.99 seconds. Okay, so we got our time value. Now we get to plug it back into this formula. And we can solve for our delta x. So I'm just going to go ahead and rewrite it. So we have delta x equals bt plus 0.5 at squared. Okay, so since we don't have an acceleration component for our x component, we can go ahead and cross that out. So now all we have left is the change in x equals bt. So rewriting this, we have our x2 minus our x initial, which is going to be 0 because it's our starting point. And we're going to set that equal to our velocity in our next direction, which is 14.9. And we're going to multiply that by our time, which is 2.99. So we have x2 equals 254.55 meters away from the cliff. And we essentially solved it. Now, going into the actual calculator, we converted our velocity into terms of meters over seconds, and then we found the y component using sine of 5. We did the same thing to find the x component of our velocity using cosine 5, and from there we got the 14.94, and we got 1.31. Okay, so from there, we used this formula and rewritten. This is going to be this formula, and this is for the y component. And we use this just to solve for our t value, and our t value was 2.99. And from there, we were able to go back to this formula and solve for our change in x. So from there, we went ahead and plugged in our time and velocity, and we know that there's no acceleration in the x component, so we can just cross that out and do vx times 2, and we get 44.73. So we're pretty close.